Hello, I am No Young Jin, responsible for developing cloud security products. In this session, I will delve into the technical aspects of container security in more detail. The agenda is as follows. We will proceed in order to discuss what is important in container security, what issues exist, and what container security measures need to be applied to address these issues. First, since containers primarily run in the cloud, we need to look at the cloud situation. As you all know, the cloud is continuously growing. While many are aware that the cloud is growing, AI is at the center of this growth. Since AI services are naturally provided through the cloud is expanding even more based on AI. In fact, some experts install open-source models like Llama on their PCs with GPUs to run AI, but most of us, regular technicians, experience cloud AI through platforms like ChatGPT or Gemini. Therefore, the cloud is growing significantly based on AI, and at the center of this growth are containers. In fact, cloud and containers are inseparable, and you cannot exclude containers when deploying applications in the cloud. So, let's briefly touch on why containers are important. First of all, containers are highly scalable because they are designed with scalability in mind from the very beginning. The reason we use containers in a cloud-native environment is that each container represents a service. If one container can accommodate 100 users, then if the number of users suddenly increases to 1,000, we can launch 10 containers, and if it increases to 10,000, we can launch 100 containers. Therefore, containers are very scalable. Additionally, they are lightweight. Containers are typically created for a single service, and the best practice is to ensure that a single service operates within a single process. Since this single process usually opens only one or two ports to function, most containers are very lightweight, allowing them to be launched and terminated immediately, which offers several advantages. Moreover, while containers usually run on Linux servers, x86, and Intel-based servers, they are increasingly being deployed on ARM architecture as well. For those using Apple products, Apple Silicon is based on ARM architecture, right? ARM refers to Advanced Risk Machine, and its advantage lies in having fewer instructions, making it very fast and lightweight. It is low power and has the benefit of being able to use existing containers in such environments. Therefore, containers have the advantage of being usable in any environment. So, what about containers in terms of security? Fundamentally, containers have excellent isolation capabilities. Therefore, one container is thoroughly isolated so that it cannot access or interfere with other containers that are on the same server. Since it is common to create containers for each service, the ports are not open in a way that resembles a monolithic application, resulting in a very narrow attack surface. Therefore, it is an environment that is not easy for attackers to exploit. The most important aspect is that the control and limitation features are outstanding. Through this, operators can utilize containers very efficiently, controlling CPU usage, memory allocation, and even disk access. This is one of the advantages of containers. So how is container security implemented? In fact, we as users do not directly handle container security. Containers utilize kernel, security-based protection features for security. Therefore, by controlling user permissions, which is a basic security feature in the Linux kernel, through namespaces and cgroups, containers are protected from security vulnerabilities. In terms of user permissions, by not granting administrative rights and only allowing limited permissions, we control the containers to prevent security incidents. To actually implement this, there is a feature called Secure Computing Mode, which controls access to kernel APIs. Typically, among the APIs that the kernel has, recent Linux versions have around 300 APIs. In the case of Docker, which we commonly use, it restricts access to only about 40 kernel APIs, when general containers access kernel APIs through Docker. This restriction provides safeguards to prevent containers from interfering with each other. The namespace feature performs isolation. For example, If I have a process ID of 1 inside a container, the adjacent container can also have the same ID. However, from the host's perspective, the host sees the first container as, say, 345, and the second container's process ID 1 as 356, and so on. This way, within the container, it creates an isolated environment as if I am the only one using the system. This isolation is implemented through namespaces. C groups or control groups refer to the control and limitation functions mentioned earlier. Therefore, it is designed to control the operation of containers by utilizing the basic security features of the kernel, which allow for controlling CPU usage up to a specific limit, restricting memory usage to 512 MB, and managing disk I/O. So, does the basic security feature of these containers make our container security perfect? Of course not. That's why we use supplementary security products. So, if we look at the current issues in general container operations, containers, as you all know, mostly start as open source and are structured in a way that combines our created source with it, or combines our created containers with open source containers. Open source may have vulnerabilities, and there are cases where the source code we create has unintended vulnerabilities introduced by those who develop open source software. In cases where vulnerabilities are intentional, they could be considered Mariana attacks. This raises concerns about potential attacks on the supply chain, highlighting the issues posed by external environmental factors. The second issue is network risk. As mentioned earlier, containers operate in an environment where only specific ports are opened. However, from an external perspective, there are instances where, instead of just opening those specific ports, all ports are opened, allowing access and increasing risk. When operating containers, you will typically do so based on Kubernetes, and naturally, when using Kubernetes, you will use CNI for traffic distribution. CNI, which stands for Container Network Interface, acts as a plugin that distributes the numerous IPs held by containers based on customer requests. Since it is a plugin located at the junction where all network traffic passes, there is a risk of attacks through any weaknesses or vulnerabilities that may arise here. And finally, in fact, this is the biggest threat. Containers are originally designed to run only in user mode, but there are attack methods that can escalate privileges to gain root access. This can lead to scenarios where a container is not isolated and can access adjacent containers. Additionally, there are various attack forms that can render a container ineffective, such as DDoS or DOS attack. So, how should we defend against such attacks? This is a very recent announcement. In the month of August, an attack was officially announced that was presented last month. It is called the Slubstick attack, and it was introduced by a prestigious university research institute located in Austria. This attack is not a mere vulnerability. It combines multiple vulnerabilities to exploit a structural flaw inherent in the system kernel. This flaw is a result of the kernel's unavoidable structural limitations in managing the actual heap memory. When we develop applications, we allocate memory and free it when done. But developers seldom fill the memory they used with zeros before freeing it. There are also cases where the double freeing of memory occurs, such as calling free twice on the same pointer, or reusing freed memory. While the kernel's memory heap management system has some structural flaws, these flaws are not inherently vulnerable enough to lead to successful attacks. This means that even if someone is lucky enough to seize the freed memory in the system, the chances of success are very low. The issue is that the research institute has managed to increase the success rate from below 5% to over 90%. So, this was announced in August. And even now, there are reports on Twitter and blogs about hacking through slapstick attacks, highlighting vulnerabilities. If such an attack occurs, it can lead to container escape or root access, as mentioned earlier in the runtime environment. This means that I could potentially carry out such attacks using a container operating on an actual server. Of course, this is not an easy attack at all. As you can see below, it has been discovered that this occurs in Linux kernel versions 5.19 and above 6.2, and it happens when mixed with the existing 9 CVs during an attack. So, how exactly should we prevent such occurrences? In fact, we are in an environment where we have no choice but to use a lot of open source. We can't develop all the code ourselves or build the web server ourselves. But even when we write such code, we just use Nginx when we use open source. So we often use Nginx without knowing what software it consists of, just treating it as a black box. In fact, the biggest problem when using open source is that we don't know the contents of that open source well, and the lack of visibility is an issue. Open source does have vulnerabilities. However, if I run a vulnerability check today, and it shows that it is safe, can we be sure that this open source will be safe tomorrow? It is possible that vulnerabilities have not yet been discovered. What was found today may be discovered tomorrow. This means that open source software that was safe today could be vulnerable tomorrow. This is a significant issue, and it is unintentional. Intentional threats include things like Mariana backdoors or cryptojacking. Nowadays, there are quite a few cases where coin miners are embedded in open source software, and many have been discovered. Therefore, we have been continuously contemplating how to manage such open source software. Recently, legislation has begun in the US, and the management of SBOM has started to gain attention. Many of you may be familiar with SBOM. Originally, when we make a car, it contains thousands of parts. Those tens of thousands of lists are originally called BOM, which stands for Bill of Materials. Among them, the software-based BOM is referred to as SBOM. So, if the software is Nginx, does that mean Nginx alone contains everything? You must have used some software to develop it, right? SBOM is about listing everything, starting from the libraries contained within. Therefore, SBOM plays a role in ensuring visibility for the software that I did not develop. So, as you can see in the picture on the right, when you generate an SBOM, it naturally includes the name, any vulnerabilities, the supplier, the version, the download URL, when it was built, whether there are dependencies, and whether the license is BSD or GPL. It also contains a unique identifier value that can hash the SBOM itself. Currently, about 3 SBOM formats are widely used as part of the defector standard. In the case of CycloneDX, it is in a very lightweight digital format, while SPDX supports various formats, and SWID is an internationally standardized SBOM. However, the SBOM is currently starting, with legal formalization in the US, but we are also actively working on it with various organizations, including KISA, and it is being done in China and other countries as well. This could potentially become a trade barrier in the future. This means that China has created an SBOM format that starts with C, which is a new format used in China. Therefore, to deliver software to China, it must be modified to fit that format. If there are items in that format that are not in our existing SBOM list, we will need to create those as well. Therefore, there is a perspective that we need to proactively engage in this, because it could later be utilized as trade barriers for the export and import of software. If we take a brief look at how SBOM works, the SBOM is scanned by a scanner called the SCA scanner. So we scrape everything that is configured inside and utilize it. Let's see what the content is. Usually, open source software like Trivi or Shift operates as SCA scanners. Then it generates an S1 list and outputs it in the desired format. This can be submitted to an organization that wants to purchase some software, or if there are vulnerabilities in my operations, I would need to apply patches. After applying the patches, I need to run the patched software. But for those who have operated systems, can you immediately run the patched version the next day after a vulnerability is discovered? Of course, there are cases where the patch is very recent, and the software I was using was also quite recent, so it can be simply patched. However, if there has been a long gap and I haven't had time to apply patches, then applying a patch might require modifications to the software, and those modifications could start from parameter adjustments, right? If a library suddenly goes missing, it means that significant modifications will occur. Of course, there are such issues, and there are situations where patches cannot be applied immediately. This aspect exists, and the SBOM itself is a process for proactive defense. Therefore, since defense is also necessary in a running state, SBOMs serve their roles, and runtime security is needed for runtimes. Thus, we must go beyond SBOMs and ensure that we implement runtime security. Runtime security is a security product that monitors, controls, and blocks in real time in the live operational environment where containers are running. So, runtime security, in fact, the software we usually use for antivirus and malware detection is all runtime. It's about control in a real-time environment where something won't execute if it's a blocking code. Now, in the runtime environment, as I mentioned earlier, vulnerabilities have emerged, but if we haven't patched them, we can't just leave them as they are. So, we proactively block attacks related to those vulnerabilities in real time. This way, even without patching the vulnerabilities, we can achieve the same effect as if we had patched them through prevention measures. And, this is a file that I am not very familiar with, but someone is trying to execute it. In that case, there are methods to block that execution and control it. Additionally, on the network, it seems that this is a network packet containing attack patterns. Therefore, we can either block it or control it through monitoring. This allows us to defend against real-time attacks. Furthermore, to enhance container isolation, there are various methods to activate access control. Now, how do we implement runtime security? The screen on the right shows the container operating environment I mentioned earlier. Runtime security is configured to run containers on a security module with administrative privileges. Since we need to ensure container security and the environment is container-based, we can launch the security product as a container. This means that while it runs as a container, it has privileged access and performs administrative functions, allowing direct access to the kernel. By directly observing the kernel, we can monitor all passing packets and the entire execution environment, controlling system call access, file systems, and various network traffic. This creates a powerful environment for control. However, this power comes with risks. Since it operates in kernel mode, the control over kernel mode is strong, but if mismanaged, it can lead to significant performance overhead. Additionally, because it runs within the kernel, there are dependency issues that must align with the kernel module's version. The biggest issue is stability. While the company developing the security module must ensure it is developed safely, human error can occur, so that aspect must be well controlled. Everyone is likely aware of the incident that occurred in July, the CrowdStrike BSOD screen. I doubt anyone here hasn't seen it, as it was everywhere in July. It was around early to mid-July when CrowdStrike's security product, Falcon, which is well known, performed a security module update that resulted in a BSOD. At the time, there were news reports questioning whether it was a cyber attack, but ultimately, it was due to the sensor csagent.assys of the Falcon security module owned by CrowdStrike. A crash occurred due to a malfunctioning file, which triggered the BSOD. While one might typically think that turning the device off and on again would resolve the issue, in the case of this security module, it starts up first before any other processes. It wouldn't be acceptable for someone like Maria to rise before oneself. Therefore, the agent with this ongoing issue has always managed to appear first, by manipulating the system to ensure they are the first to rise. As a result, even after rebooting, the BSOD kept appearing repeatedly, and eventually, I had to enter safe mode, and delete the CS agent file located in the system directory to stop the BSOD from appearing. This meant that remote patching was not possible, and I had to go to each individual service server to perform this task. At that time, this issue likely had not been resolved yet, affecting around 8.5 million servers and PCs. This caused a tremendous shock to services worldwide. In some ways, domestically, there wasn't much use of the CrowdStrike product, so it didn't become a significant issue here. But globally, it was a very big problem. Of course, the root cause is ultimately the failure to conduct thorough software testing. But does thorough software testing solve everything? There will always be unavoidable aspects due to human mistakes. This is because we use something called a kernel module. Kernel modules are originally needed for certain security features in this kernel. Then, if the Linux Torvalds group adds those security features to the kernel, it usually takes about 3 to 5 years for the kernel to thoroughly test the safety of those features before they are implemented. So, security companies can't wait for that. Therefore, they perform operations using something called an open kernel module. However, if there is a failure in the kernel module, the entire system crashes. So, while this incident is not the sole reason, the increasing spread of cloud has created a need for alternatives in various situations, and a recently popular method is eBPF. Of course, there are people here who are quite familiar with eBPF, but for those who are not, let me explain a bit. eBPF originally stands for Berkeley Packet Filter, which was created for the purpose of capturing packet dumps when we perform TCP dumps in Linux. eBPF has evolved from BPF to extended BPF. As its use cases have expanded, it has been widely used in security monitoring. The greatest advantage of eBPF functionality is that it directly addresses the shortcomings of kernel modules that I mentioned earlier. What this means is that when this code is executed through eBPF, it is not just a simple list of code. It is written in C and converted into bytecode like Java, running in a virtual machine within the kernel. This means that if an error occurs, we can simply kill the virtual machine inside the kernel without affecting the entire system. Ultimately, it provides a very safe way to use it like a kernel module. Moreover, running it in a virtual machine is even faster than running a kernel module. This is because when the kernel runs, various module functions are executed simultaneously through time slicing. However, time slicing involves context switching, which can lead to cache misses. In contrast, this limits context switching within the virtual machine, making it faster than kernel modules. Therefore, eBPF is increasingly being used by security companies to implement security measures, and companies like ours, AhnLab, are naturally implementing it in this way. Thus, we can say that eBPF is essential for applying strong security safely. So, in a real cloud-native environment, is eBPF the only answer when we talk about runtime secrets? That's not the case. Depending on the environment operated by you at the client company, you should be able to apply the same security features in a way that is very suitable for your needs. Most of you will deploy containers using Kubernetes pods, but I need different configurations for each pod I deploy. I don't want to apply the same security settings across the board, and I want the security modules to be fully containerized so that I can terminate them whenever I want. I also want to limit the security modules to use only 100 megabytes of memory and create an environment where they don't crash or generate BS errors. In such an environment, you can utilize the sidecar model in Kubernetes to attach security modules to each container, allowing for tailored operations. Additionally, I prefer centralized control, where I can safely manage all container modules running on the entire server using a module like eBPF with the same rules. The important thing is that security products must be adaptable to various environments. I've only shown 2 representative environments, but in a Kubernetes service environment, security requirements must be met in diverse ways to ensure an appropriate security environment. I've mentioned several points regarding container security, and to summarize, in a cloud-native environment, it is essential to use containers, which are crucial building blocks, like Lego blocks. To secure these blocks, various security policies must be established, with the first being pre-execution security. It is essential to identify any vulnerabilities from the software development stage in order to enhance the visibility of the SBOM and protect the software supply chain. Additionally, areas that cannot be mitigated must be addressed by blocking dynamic attacks during runtime security. This is also a very important area. For example, no matter how good the runtime security is, if you experience a BSOD and everything crashes, it becomes meaningless. In that regard, there may be cases where kernel module security is desired, so that should be supported as well. If you want to use eBPF, then eBPF security should also be applied. And you need to use security products that can support various environments. Therefore, I hope that the key keywords I have mentioned so far, SBOM and security using eBPF, are well utilized so that the services you are currently operating or will operate in the future can run in a safe environment. This concludes my presentation. Thank you.